Okay, so let us now continue with our answers to those whys, those gaps that we have seen in the proof of Riemann's theorem. We have already answered a couple of them, but there are others. So let us now see what the next why is. The next why is this. The map which maps J onto Nj is surjective, it's an onto map. Why? Recall that we have already proved that this map is injective, and besides that we have also proved that those two cases that we see in the definition of the sequence Ni in the proof of Riemann's theorem, case 1 and case 2, both of them occur infinitely many times. So these are the whys we have answered. Now let us see what we can do with this one. So we start our argument like this. Let Nki, where I varies over all the natural numbers, be the subsequence of Ni consisting of those terms that belong to the set A plus. We already know that the definition of Ni depends on case 1 and case 2. Since both the cases occur infinitely many times, so there are infinitely many Ni's coming from the set A plus and also infinitely many Ni's coming from A minus. And in fact, each Ni comes either from A plus or A minus. In fact, if at the stage of choosing Ni, that condition that you have, if that condition falls under case 1, if that sum is less than L, then your Ni comes from A plus. But if that condition is that the sum is greater than or equal to L, then your Ni at that stage comes from A minus as the minimum of a set. We already know these things. So that is why there are infinitely many Ni's coming from A plus, and the ones that come from A plus are precisely this. So this is a subsequence of this, and because of for this we need this fact. Recall that case 1 occurs infinitely many times. Okay, so now just simply put, this consists of those Ni's that come from A plus. That's it. Now our claim about this subsequence is this. We claim that this subsequence is strictly increasing. And now we are going to prove this claim by induction on I. That is the most natural approach. So the first inequality that we need to prove, which will be the basis for our induction, is nk0 less than nk1. That means the case when I is equal to 0. We know that. So now, without thinking too much about what nk naught is or what it may be, we just simply use the definition of nk naught itself. It is the minimum of the set of all elements in A plus n such that n is not equal to ni for all natural numbers I less than k0 or k0. Okay, so this comes directly from the definition of the sequence ni. And oh, by the way, why are we not having a minus here? That is because we already know that nk naught is coming from A plus. In fact, all these nki's are coming from A plus, and in fact they are precisely the ones that come from A plus. Okay. Now this is fine. So let it just be like this, and we consider something else about these i's that are less than k naught. If we suppose ni belongs to A plus for some I less than k0, then ni would be equal to nkj for some natural number j. But why? That's because we know that any ni that comes from A plus appears here. So if you have one such ni for this type of I, that also should be some nkj for some j. That's what we have written. Now, since ki is a subsequence of I, since ki is a subsequence of I, the sequence of natural numbers. Why? Let us first of all think, why is that so? That is because we have said that this is a subsequence of this. So the subscripts ki should form a subsequence of the sequence of all natural numbers, and that is why and now we are going to write what is a consequence of this. We have this. That means, being a subsequence of the sequence of natural numbers, it is increasing. No matter what the ki's are, the subsequence is strictly increasing, because the original sequence of all natural numbers is strictly increasing. Okay. But then, what is the consequence of that in turn? That means, because I is less than k naught, I is not equal to any kj. In particular, I is not equal to this kj. Naturally, I lies on this side and kj is here in this list. So I is not equal to Kj, but I and Kj are different, whereas Ni and Nkj are the same. This violates the fact that the map which maps J to Nj is injective. We have already shown that that is one of the whys. This contradicts the fact that the map is injective. Do not confuse this J with this specific J. Okay, here J is something, some specific J, here J is just any J. So that means we cannot have any such thing. So for any natural number I less than k naught, Ni does not belong to A plus. That means this condition that you see here is actually true for all elements of A plus. If our I is less than k naught, then Ni does not belong to A plus. So, and that itself means that the set that you see here is actually nothing but A plus itself, the entire A plus. So, should I write that, or do I need to write something else? Or we can at least write, so the last supposition is wrong, and hence for all I less than k naught is A plus itself. Thus, now Nk naught becomes something very simple. Nk naught is nothing but the minimum element of A plus itself. Okay. Now, since Nk1 belongs to A plus and Nk0 is the minimum element of A plus, so Nk0 will be less than or equal to Nk1, and then you apply the injectivity of this function and claim means conclude that Nk0 is less than Nk1 using the fact that this is injective we thus have is less than Nk1. So this is the basis for our induction, and now we are going to assume the induction hypothesis. If you want, you can mention this forms a basis for an induction. which it's obvious what induction we are trying to achieve here. Now assume nk0 less than nk1 less than nk2 less than nkj. Yeah, I think I have gone that far. I have written one more term, nkj minus 1, that is less than nkj, for some positive integer. I don't know why it is the case that the more I write, the worse my spellings get. Nkj for some positive integer j. This is our induction hypothesis. So that means we are using strong induction. Although we won't actually need to use these inequalities, but we are just simply considering it. If you are unsure of how the induction step can be achieved when you are trying to carry out one such induction, it's always safe to assume as much as you are allowed to assume in the induction hypothesis. That is, always use strong induction, no matter what. Unless, of course, your thing that you are trying to prove by induction is something very simple. But in some such uncertain cases, you use strong induction. If it turns out that you don't have to use these things, then there is no harm, because it's also a legitimate proof. Now, we have this next thing that I am going to write may be a little confusing, but we will of course understand it. In fact, I myself got confused today when I saw it, and I in fact forgot how I thought about it, but then it came to me. So it is this nkj plus 1. nkj plus 1 belongs to this set and nkj is the minimum of this set. There is no problem with this one, because this is what nkj means. And also, again I am saying, repeating same thing, but still that we are consistently using a plus because all nki's are coming from a plus, that's why. But what is not so clear is this: how exactly is nkj an element of this set? We have already gone through one such argument, but still it has been some time. Last Sunday we did it, so let's just see it once more. nkj plus 1 is by definition what? It is the minimum of this set. Less than kj plus 1. Okay, so that means it is the minimum. Now we can write this set as a difference of two sets. From A plus we can remove, we are actually removing these elements n0, n1 and so on. Before we get to kj plus 1. Note that before we get to kj plus 1 means I will get till kj plus 1 minus 1, because I does not have to have this form kj. I need not be equal to kj. I is just some natural number less than kj plus 1. In kj plus 1 minus 1 yes, that's what it means. This theorem, so many suffixes now get confused. You note carefully that 1 is being subtracted from the suffix kj minus 1. I think that is clear. Okay, so n kj plus 1 is the minimum of this set. Now, this set is a subset of this set. Why? You see that this set is a subset of this set. If you just think of this set and forget about a plus for the moment, then this set is a subset of this set. Why? Because before you get kj plus 1, you get kj, and that also because of what? The sequence kj is strictly increasing. So as you increase your suffix from 0, 0, 1, 2, 3 like that, at some stage you are going to get kj, and then after that at some stage you are going to get kj plus 1. Maybe kj plus 1 is not the integer next to kj, that is kj plus 1 may not be equal to kj plus 1, but maybe a little further away, but it will lie to the right of kj plus 1. So that means kj minus 1 is an integer, is a natural number less than kj plus 1 minus 1, because this is less than this, and that's why this suffix appears before this suffix, and that is why this integer n kj minus 1 appears here somewhere. After that there are some things, and among those some things this is the last thing, so that's why this set is a subset of this. But when you consider such differences, the subset relation gets reversed. This is just like you have this ordinary inequality. When you multiply by minus 1, it gets reversed. Something similar happens with sets also when you consider differences. So that's why you have this containment. But then this means what? N kj plus 1 being the minimum of this set is in particular an element of this set. So being an element of this set, it also has to be an element of this set because this is a subset of this. So our final conclusion is this. and the set that you see here is nothing but this. That is where we are subtracting from A plus, removing from A plus those ni's for which I is less than kj. So I will go from 0 till kj minus 1. So now that we understand this, so what is the relationship between nkj and nkj plus 1? This is the minimum of this set, whereas this is just an element of this set. So nkj will be less than or equal to nkj plus 1. Hence, or so, nkj is less than or equal to nkj plus 1. And just like before, using the fact that our map is injective, this inequality becomes strict. Using the fact map is injective, we have this. So by induction, our claim is established. So much for just proving that the subsequence nki is strictly increasing. But what are we going to do with this information? But before we see what, let us also mention the other thing, the other counterpart of this subsequence. One can similarly prove that if nmi is the subsequence of ni consisting of those ni's that come from A minus, then this subsequence is also strictly increasing, just like nki. That lie in A negative, then nmi is less than nmi plus 1 for all natural numbers I. And also do not forget that this is also a subsequence of this because case 2 occurs infinitely often. Recall that infinitely often or infinitely many times. same thing. Okay, so now we know at least that these subsequences, see, we don't really know which ki's are giving us the nki's and which mi's are giving us the nmi's. That means we don't really know which ones are coming from A plus and which ones are coming from A minus. The only thing we have known so far is that infinitely many ni's come from A plus, forming the subsequence nkj, and infinitely many come from A minus, forming this subsequence. But now we have managed to show that if we look at them, look at any one of them, say the subsequence nki, then its terms are strictly increasing. Similarly, if we look at only the ones that come from A minus, nmi's, they are also strictly increasing among them. That much we now know. Okay, so now our aim is something else. We need to prove that this map is surjective. That means that this map gives us all the natural numbers. That's what we have to prove. That means every natural number is equal to nj for some j. That's what surjectivity means. Suppose that is not true. So that's what now we are going to do. Okay. Now let P belonging to A plus be any element. Now in the process of choosing the terms nkj, maybe it's the case that some element from A plus has been left out. If that happens, then the sequence ni cannot give us all the natural numbers because that p will be left out. In choosing these ni's, maybe it's the case that ni is not equal to p. In the process of choosing minimum from those sets, maybe p has been left out from that process. Then that will go against surjectivity. So that is our supposition. Suppose that P is not any ni. P does not belong to the set of all the ni's. Then what happens? This part is very critical. Okay, so let me just see what I have prepared here, and then I will try to explain myself. I cannot remember this part. So after that, what I have done since, okay, and in my argument, if I have made any mistake, I mean in this part that now I am going to write, it will come out now. Hopefully there is no mistake. Let's see. Since nk naught is equal to the minimum of A plus we must have nk naught less than p. Why? Because we are taking p from where? A plus, and also we are assuming that p is not equal to any ni. And since we know that nk naught is actually equal to the minimum element in A plus, so p has to be greater than or equal to nk naught, but it cannot be equal to nk naught also. So p is strictly greater than nk naught. Okay. Now since the sequence nki is strictly, well, we do not actually need to use the strictly increasing nature of this sequence to now write what I am now going to write. Instead of writing this, let us write this instead. Since the map J to nj. No, but then if I write this, then I won't exactly get what I'm trying to get. Oh, okay. So, okay, fine. Let us go back to that itself, what I was writing right now. Since the sequence nki is strictly increasing, we have p less than nkj for some positive integer j. You see, p is coming from A plus, so p is some natural number after all. And the nki, this sequence has infinitely many distinct natural numbers, and that too it's increasing. So that means at least one of them has to exceed p. Infinitely many of them cannot be less than p, because anyway there are only finitely many natural numbers less than p. So the set of those j's so the set of the positive natural numbers I for which nki exceeds p is a non-empty set, because this j, for example, is an element in this set, is a non-empty subset. I am also watching carefully the steps. You also please watch. If you spot any mistake, please let me know in the comment section. Is a non-empty subset of n, and it is because of this fear of making any mistake that I am writing things so elaborately. So because it's a non-empty subset of n, it will have a minimum element by the well-ordering principle. Thus q equal to the minimum of this set exists. That means q is the smallest I which is a positive integer such that nki is greater than p. So far there is no problem. But okay, next what I have written, but p belongs to, okay, I have written something. Let me first simply copy it and then see what I have written. So what I have after this is these two things. P belongs to the set of all elements n in A plus such that n is not equal to ni for all I less than kq and nkq, and nkq is the minimum this set, okay. Where is this coming from? P belongs to the set of all n belonging to A plus such that n is not equal to ni for all I less than kq. Why? Why do we have this? Suddenly I cannot understand why we are having this. For P to be here, what is the requirement that P is not equal to any of these things? N kq minus 1. Yeah, at this last stage, if I can't decipher this, then what the hell am I doing? P is not equal to any of these integers, but why? What happens if P is equal to any of these ni's? What goes wrong? Oh, okay. How foolish. I forgot the main assumption on P. The main condition on P is that P is not equal to any ni. So in particular, P is also not equal to this particular ni's. In fact, P cannot be equal to any ni. So that is why in particular, P also belongs to this set. And anyway, P is coming from A plus. So that explains why we have this. It is because of this condition. And the thing that we have chosen P from A plus in the first place. And nkq is of course by definition this. Okay. So now what is the consequence of this and this? P is an element in this set and nq is the minimum. Thus nkq is less than or equal to P, but it cannot be equal to P again because P is no Ni. So P must be strictly greater than nkq. But what does this tell us? This tells us that since Q is the minimum of this set, Q in particular belongs to this set. That means Q is an I that satisfies this inequality. Which contradicts this. Okay, so we have arrived at a contradiction. So our last supposition is wrong, i.e. P must belong to this thing. But P was what primarily we chose P to be any element in A plus. So every element in A plus belongs to this. Thus A plus is a subset of the set of all the terms in our original sequence Ni. Similarly, one can prove that A minus is also a subset of this. Hence, in the set of natural numbers, we have already seen that this is equal to A plus union A minus. This fact we have seen even before having the statement of Riemann's theorem. In that lemma itself we saw it. Maybe it was a proposition, I don't remember, but that other thing. So this is now going to be a subset of the set of all Ni's and this gives us this fact that we have been seeking, that these Ni's are actually all the natural numbers. So that means the function or the map that maps J into Nj is surjective. Thus, is surjective. Note that having proved that this map is injective, which we already saw before, and now that it is surjective, it now becomes a bijection or a one-to-one correspondence from the set of natural numbers to the set of natural numbers. And using this one-to-one correspondence, we can now arrange the terms of our original sum, summation an. So this is the answer to this y. There are two other y's of which we are going to see another one, but that last one we are going to see next Sunday. The other y is this. We have this limit. So let's now answer this one. Now we already know one such limit. We already know that limit of an as n approaches infinity is 0, and this comes from the hypothesis of Riemann's theorem. Riemann's theorem gives us what? What is the ingredient of Riemann's theorem? That this is a series that is conditionally convergent but not absolutely convergent. That means after all it is convergent, but if you replace the an's with their absolute values, that series is divergent. Now we know a necessary condition for such convergence, and that condition is this. It is that zero test of convergence, that thing we have. So that's why we already know this. Now suppose this is not true, and in particular we can suppose this. Suppose, but before we consider any such supposition, let us take our ubiquitous epsilon. We always have epsilon. Choose any epsilon greater than 0, and now we make that supposition. Suppose that the absolute value of Anj is greater than epsilon for infinitely many natural numbers j. Say we have made this supposition, and now we are going to see what consequences we have of this supposition, that there are infinitely many natural numbers j for which this absolute value is going to be greater than epsilon. What this means is that say this is your 0 on the numbered line, and say this is your open interval centered at 0 and having length 2 epsilon, that means epsilon on either side. This supposition means that infinitely many terms of the sequence A and J lie outside this interval. Maybe infinitely many are also lying inside this interval, but infinitely many are also lying outside this interval. That's what this supposition means geometrically. Then what happens? Since these nj's are after all nothing but some natural numbers only, so that means that this is also greater than epsilon for infinitely many n's. But you can immediately see that that is a problem. But this contradicts this limit. Why? Because this limit says that no matter what epsilon is, that means no matter how large or small this interval is, at most finitely many ANs can lie outside. All the rest of the ANs have to lie inside, because that is the only way we have convergence, right? So you consider one region around your limit. The region fails to capture at most finitely many terms. So you do not think about them. It's like zooming in on a picture. So your zoom area is this much. Then you increase your zoom. You get to a smaller interval. That again, maybe it leaves some ANs outside, but again, finitely many. All the rest of the things of the sequence lie in this. That way we have convergence. That is the nature of convergence. That's what convergence means. So we have a contradiction here. So this supposition is wrong. You see, the definition of convergence of sequences and also convergence of functions, we are going to come across those things. All of these things involve inequalities and epsilon, because we are using algebra to try to capture infinity, which cannot be done ordinarily. Something itself has to be infinite in this process, and that is why you do not see things like this. Say the difference between an and your limit becoming equal to something. This is not something that can capture the idea of limit, because it's an infinite process. That is why instead of that you have approximations which tell you how near the ANs are to L, and not one or two such approximations, but infinitely many of them. Anyway, so now our last supposition is wrong. That is, at most finitely many natural numbers j are there for which this is greater than epsilon. That means because there are only finitely many such j, there will be one maximum such j. So there is a largest j such that Anj is greater than epsilon. That means if you increase the value of this suffix of suffix more than j, then this inequality is no longer true. Thus, Ani is less than or equal to epsilon for all I greater than or equal to j plus 1. Now you see how it looks. The size of Ani, which you can, in fact you should interpret this thing as Ani minus 0. The distance between Ani and 0 is less than or equal to epsilon for all I greater than or equal to j plus 1. And since our epsilon was arbitrarily chosen in the beginning of this process, so for each such epsilon there will be a natural number for which these things will happen. Hence, this is equal to 0. And the last pi that I won't do today, it is just this, which is the final step in Riemann's theorem. This thing. So now once we prove this, things are going to be over. It is that this sequence of natural numbers has all the natural numbers, and in such a way that it has all the natural numbers precisely once, and that is why this map is injective as well as surjective. What it does is that it rearranges our original series. The original series is this, and the rearranged series will be this, Ani. Things have been arranged in such a manner that this is now converging to the natural number L, which was chosen in the beginning of the proof itself. So that means, although the original series being convergent, it converges to something, but being not absolutely convergent, its nature is such that there exists a rearrangement for any given real number so that that will converge to L. That is Riemann's theorem. So this part we are going to do and complete the proof of the theorem in its entirety next Sunday. And I am stopping the video here itself. and our next upload is this coming Tuesday, and the cycle has been completed once more. So on Tuesday we are going to go back to group theory from Herstein's Topics in Algebra. So see you on Tuesday with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.